Welcome to Nanopedia.
Welcome. My name is Carrie Donnelly, and I'm the director of the Chapel Hill Analytical and Nanofabrication Lab, or CHANNEL, at the University of North Carolina. Today, we will be talking about electron beams. This is an image of the RTNN logo taken with an electron microscope. Notice the scale bar in the bottom right corner. As the microscope zooms into the features of this logo, you can see that there is another, much smaller UNC logo also present. This one is only about 200 microns wide, and the features are even smaller. If we continue to zoom in, you'll see another logo. This one is of the famous Old Well landmark at UNC. This logo is only 4 microns wide, and the features within it are even smaller. The electron microscope clearly has better resolution than the light microscope. Electrons are the elementary unit of negative charge. You use electrons on a daily basis when you use electricity in your home. Anytime you plug something into the outlet at the wall in your house, you are using electricity. The flow of electrons along power lines also carries electrical power into your home. But electrons can also act as waves. The wavelength of an electron is described by the equation shown here. The wavelength, lambda, is equal to Planck's constant divided by the mass of the particle times the velocity of the particle. Since Planck's constant and the mass of an electron are known, we can determine the wavelength of an electron if we know how fast it's traveling. The faster the electron is traveling, the smaller its wavelength will be. Electrons can move through wires. For example, when electricity comes into your house from a power station, or when electricity travels from an outlet to a light bulb. Electrons can also travel through air. An example of this is lightning. Lightning is the result of electrons moving between a cloud and the ground as a result of a voltage. Electrons can also move through vacuum, and this is what happens in an electron microscope. Since electrons are negatively charged, we can cause them to move by applying a voltage. The velocity of an electron depends on the voltage used to accelerate it. For example, if we were to apply an accelerating voltage of 100 kilovolts, the electron would have a velocity of 1.6 times 10 to the 8th meters per second, and a wavelength of 3.9 picometers. 3.9 picometers is 0.0039 nanometers, which is really small. For example, the oxygen molecules in the air that we breathe are composed of 2 oxygen atoms connected with a double bond. The distance between these 2 oxygen atoms is about 0.1 nanometers. 3.9 picometers is much smaller than that, and also much smaller than the wavelength of visible light, which ranges from 400 nanometers to 700 nanometers. Therefore, when using electrons to image, we should be able to resolve much smaller objects. Now that we have talked about how we can move electrons, and that they should be able to allow us to image very small things, we should look at how electrons interact with a sample. Electrons that are accelerated towards a sample will enter the sample and interact with the electrons already present. Some of the incident electrons will scatter or bounce around in the sample. At each scattering event, they will lose some energy until they run out of energy and are left stuck in the sample. These electrons are captured by the sample. Some of the electrons from the incident electron beam will scatter in the sample and will eventually make their way back out of the sample. These are backscattered electrons. Sometimes an incident electron will strike an electron already present in the sample and knock it out of the sample. This is called a secondary electron. Both secondary electrons and backscatter electrons can be used in scanning electron microscopy, or SEM. After a secondary electron has been produced, a byproduct of the relaxation process is the production of X-rays. We can measure the energy of these X-rays in a technique called energy dispersive spectroscopy, or EDS. If the sample is thin enough, around 150 nanometers or less, then some electrons will pass through the sample. Electrons that pass through the sample without interacting with it at all will retain the same direction of travel and energy as the incident electrons. These electrons are used in transmission electron microscopy, or TEM. Other electrons will pass through the sample, but will scatter either elastically or inelastically. Elastically scattered electrons will change direction, but retain the same energy as the incident electrons. These electrons can be used in a technique called electron diffraction to understand the crystalline nature of the sample. Inelastically scattered electrons will change direction and also lose some energy as they interact with the sample. They can be used in a technique called electron energy loss spectroscopy, or EELS, to characterize the atomic concentration of the sample. As you can see, electrons are very useful for a variety of nanocharacterization techniques.
Please subscribe and share Nanopedia.